Okay, this is the sixth video for Chapter 8. This is Kinetics of Substitution and Elimination reactions. We were just finishing up with the reaction coordinate diagrams in the last video. And as you can see here in this reaction coordinate, right, we were talking about how the reactants are going to form this carbocation intermediate, and this transition state up here is going to be the highest point in the reaction coordinate diagram. So this is the rate limiting step, our delta G double dagger. So we're going to go into this in a little bit more detail in this video. So as I mentioned, the rate limiting step, also called the rate determining step, is just the slowest step in the reaction, okay? And if we're looking at the reaction coordinate diagram, it's going to be the highest point, right? The highest energy transition state. So in an SN1 reaction, the slow step in the reaction is going to be this first step, the heterolytic cleavage, where the leaving group falls off. And you can see that the rate is dependent on this value K as well as the substrate. So this is where that 1 in the SN1 comes from, because it is unimolecular, because the rate depends only on the substrate. If we look at the second step, where the nucleophile comes in and coordinates with the carbocation intermediate, this step is fast. So the rate for this step here, as you can see here, depends on both the nucleophile and the carbocation intermediate. But since this one is so fast, the rate of the reaction is actually only going to be as fast as this first step. So really the rate of the second one doesn't matter because it's much faster than the first one. And so you can also get an idea of what a rate is going to look like when you have one thing involved, and that's in the first step where we only have the substrate, versus if we have two things involved. And we'll look at what an SN2 rate would look like in a minute. Okay, so why don't you try this clicker question, pause the video, and go ahead and give this clicker question a try. Okay, so hopefully you correctly guessed C. So the rate limiting step, this reaction here is it has three transition states. You can see here A, C, and E are transition states. B and D are going to be intermediates. And C is the highest point in the reaction coordinate diagram, so that would be the rate limiting step of this particular reaction. Okay, so when we were looking at the SN1 reaction, we talked about how the rate was dependent on a constant K and then also the substrate. This is an example of a first order reaction because it depends on one thing. In this case, in the case of the SN1, the substrate. We're just waiting for the leaving group to fall off. A second order reaction, and this is going to be the SN2 reaction, for example, depends on two things reacting together, R1 and R2. So the rate is dependent on this constant K, as well as whatever R1 is and whatever R2 is. So a second order reaction is going to be something like an SN2 because it depends on both the nucleophile. We could say that the nucleophile, for example, would be R1, and the substrate, which could be R2. So let's look at this, how the specific rate laws would look for these substitution reactions. And you can see here the rate for the SN1. So it depends on this constant K, and then here is the substrate. Whereas for the SN2, it depends on both the nucleophile and the substrate. So the SN1 reaction would be first order, and the SN2 reaction would be second order. Okay, so now let's talk about a little bit about what this K factor is, because this is a constant for the particular reactions, but it's dependent on various things. So in order to figure out what K is, you kind of have to go back to the Arrhenius equation. So K here, this is our rate constant for the reaction. A is a frequency factor. This is another constant. And this is just your E, right, to the power of, and EA is the activation energy, R is the gas constant, and T is the temperature. So a lot of these things, basically what this is telling us is that the rate of reaction depends on these few things here. Okay, so number of collisions per unit time, right? And that's what this frequency factor is really telling us. Also, they have to have sufficient energy, right? And that's why activation energy is part of this rate constant. And they also have to have the proper orientation. That's also part of what's going on in this reaction. So those are really what's happening in terms of reaction rate. As the molecules are coming together and colliding, they are going to, the more collisions you have, the greater the higher the rate constant, right? The faster the reaction. Also, the more of them have enough energy, you're going to have an increased reaction rate. And then if they're oriented the right way when they're attacking each other, they will also have an increased reaction rate. So in this graph, what we're looking at is the percentage of molecules able to surmount an energy barrier. Okay, and if we go back just a couple of slides here, this delta G double dagger, that's our rate limiting step, our energy barrier. Okay, so that's what those molecules need to overcome in order for the reaction to proceed forward. So to determine the percentage of molecules able to do this, you can see in blue here, this is a cold reaction. Okay, so a reaction at 0 degrees, whereas red is 100 degrees. And so what you're seeing, especially if you zoom in this area here, it's kind of a blow up of the smaller box on the lower right, that you have more molecules that are able to surmount this energy barrier when you heat up a reaction. So a lot of times what we do, if we have a reaction that's proceeding too slowly, we just give it a little bit of heat, and this helps more of the molecules to achieve that energy barrier, surmount it, and move forward. Okay, so now let's tie all of this back into our reaction coordinate diagram. Okay, in this case, this is our reaction coordinate diagram for our SN1 reaction. Right, so you can see here our rate determining step, our delta G double dagger. Okay, and this is also going to have a small k and a slow rate. When k is bigger, you have a faster rate, and that's what's happening in step 2. We also have a very small energy barrier that it needs to overcome. So this is much easier. Basically, once you've gone over this activation energy, the reaction is all essentially downhill. It doesn't have to go any higher.